Students, myself, Kote SB, Chemistry Department, Yashwantrao Chavan Institute of Science, Satara. Today, I am going to discuss about chapter number 12 from 11 Chemistry book, that is Chemical Equilibrium. Now you can observe PPT of that chapter, Chemical Equilibrium, on your screen. First, we will see what is meant by reversible and irreversible reactions. The irreversible chemical reaction is nothing but the reaction which occur in one direction from reactants to products are known as irreversible chemical reactions. For example, combustion reactions, they are irreversible chemical reactions. You can have example of burning of carbon in air or in oxygen. It is the irreversible chemical reaction. So you can write that reaction as carbon solid when it is burnt in air or in oxygen, means it reacts with oxygen to form carbon dioxide gas. So this is the irreversible chemical reaction. That means the reaction which occur only in one direction from reactants to product. That means when carbon is burnt in air, it reacts with oxygen to form carbon dioxide. This reaction takes place only in one direction from left hand side to right hand side. Okay. Second is the reversible chemical reaction. Now, what are these reversible chemical reactions? The reactions that do not go to completion in any one direction and that can simultaneously occur in both forward and reverse directions are called reversible chemical reactions. For example, you can have the reaction of formation of ammonia from nitrogen and hydrogen gas. This is the reversible reaction. Means when nitrogen and hydrogen gas combines to form ammonia gas. Again, the reverse reaction can take place. Means the decomposition of ammonia will take place to form nitrogen gas and hydrogen gas. Now we'll discuss about the equilibrium in physical processes. Equilibrium in physical process. First one is the liquid vapor equilibrium. Liquid vapor equilibrium. You consider liquid water. When it is heated, it will be converted into water vapors. So at equilibrium, the rate of evaporation will be equal to rate of condensation. Second, we will discuss about the solid liquid equilibrium. Now when ice, consider solid as ice, it is in solid state. When temperature increases, it is converted into liquid water. So this is the solid liquid equilibrium. Now at equilibrium, rate of melting of ice will be equal to the rate of freezing. So this is the solid liquid equilibrium. Third one is the solid vapor equilibrium. You consider this reaction when solid iodine it sublimates, it goes into iodine vapors, that is in gaseous state. So this is nothing but solid vapor equilibrium. From left to right, there is the sublimation of solid iodine into the iodine vapors, and in the opposite direction, there is the condensation. Now we will discuss about the equilibrium in chemical processes. The state at which both the reactants and products coexist is known as chemical equilibrium. The state in which both the reactants and products coexist, it is considered as chemical equilibrium. You can have this graph. This is the graph of concentration against time for this reaction. And another graph is rate against time. Okay. Now we'll discuss about the equilibrium in chemical process. At equilibrium, the rate of forward reaction is always equal to the rate of backward reaction. What happens at equilibrium? Both rates are equal. The rate of forward reaction is always equal to the rate of backward reaction. You can consider this reaction. When hydrogen and iodine gases, they combine to form hydrogen iodide gas. What will happen at equilibrium? The rate of formation of hydrogen iodide will be equal to the rate of decomposition of hydrogen iodide. Now, we will discuss about the rate of chemical reaction. Now, this rate of chemical reaction can be written as it is equal to minus d concentration of reactant divided by dt is equal to d concentration of products divided by dt. We will study now about the law of mass action. Law of mass action. First, we will discuss about its statement. The question may be asked, give the statement of the law of mass action, or state and explain the law of mass action. How can you give the statement of this law? The statement is given as the rate of a chemical reaction at each instant is proportional to the concentration product of all the reactants. This is the statement of the law of mass action. Okay. You see again, what is that statement? The rate of a chemical reaction at each instant is proportional to the concentration product of all the reactants. We'll see the example so you will understand the statement of this law. Now consider the general reaction. Reactants A and B combines to form product C. Now what can you write about the rate of this reaction? Expression for the rate of this reaction can be written as rate is proportional to the concentration of the reactants. Which are the reactants here in this reaction? A and B are the reactants. So rate of this reaction is proportional to concentration of A into concentration of B. To remove this proportionality sign, you can take some constant, suppose K. So we can write as rate is equal to K into concentration of A into concentration of B. Now this equation is called as the rate equation, and the proportionality constant K is called rate constant of the reaction. Now we'll discuss about the equilibrium constant. Now you consider this a reversible reaction. A plus B gives C plus D. Suppose this is the reversible reaction. So what will be the rate of forward reaction? The rate of forward reaction will be proportional to concentration of A into concentration of B. Okay. To remove this proportionality sign, we can take some constant. Suppose we have taken the constant as Kf. So we can write the above equation as rate of forward reaction is equal to Kf into concentration of A into concentration of B. What is this Kf? Kf is nothing but it is the rate constant of forward reaction. Now we'll discuss about this law of mass action. Now, in that reversible reaction, as we have seen the rate of forward reaction, similarly, we can write the rate of reverse reaction as it is equal to Kr into concentration of C into concentration of D. Now, what is this Kr? Kr is nothing but it is the rate constant of reversible reaction. Now at equilibrium, you know that what happens at equilibrium? At equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. So we can write as Kf into concentration of A into concentration of B is equal to Kr into concentration of C into concentration of D. By rearranging this equation, we can write also as Kf upon Kr is equal to Kc. These both are constant. So instead of these two constant, we can take a single constant as Kc. So Kc is equal to, we can write as concentration of C into concentration of D divided by concentration of A into concentration of B. Now what is this Kc? Kc is nothing but it is the equilibrium constant. Now consider this a general reversible reaction as AA plus BB gives CC plus DD. Now for this reversible reaction, we can write as the expression for equilibrium constant Kc equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Okay, is it clear? Now we'll see some examples. Determine the value of the equilibrium constant for the reaction. The reaction is given as A plus 2B gives 2C. Now, if 1.0 mole of A and 1.5 mole of B are placed in 2.0 liter vessel and allowed to come to equilibrium, the equilibrium concentration of C is 0.35 mole per liter. What is asked? We are asked to determine the value of equilibrium constant for this reaction. The data is given as follows. Okay. How this example can be solved? The reaction is given as A plus 2B gives 2C in forward direction. Now suppose initial moles of the reactants are given as 1 for A and 1.5 for B. Initially, there will be no product C, so its initial concentration is 0. Now at equilibriums, What can you write the concentrations of the reactants and products? You can write as concentration of A at equilibrium as 1 minus X and that of B as 1.5 minus 2X because the coefficient is 2, and for C coefficient is 2, so you can write as 2X. So these are the concentrations at equilibrium in moles. Now we can also write the concentration per liter or per cubic decimeter. As for A, we can write as 1 minus X upon 2. For B, we can write as 1.5 minus 2X divided by 2. And for C, we can write as 2X upon 2. Now, we have given concentration of C is equal to 0.35. That is 2X upon 2 is equal to 0.35. Therefore, X is equal to 0.35. So this is the concentration of C. Concentration of C is equal to 0.35. And what is about the concentration of A? Concentration of A is nothing but 1 minus X by 2. We got the value of concentration of, we got the value of X as 0.35. So concentration of A is equal to 1 minus 0.35 by 2. So it is equal to 0.325. Similarly, we can calculate concentration of B. So it is equal to 1.5 minus 2x, that is 2 into 0.35 divided by 2, and it is equal to 0.4. So for this reaction, we can write the expression for Kc as it is equal to concentration of C square, because the coefficient is 2 divided by concentration of A into concentration of B. Here concentration of, here coefficient of B is 2. So here you must write concentration of B raised to 2. You can substitute the values of the concentration of A, B and C. So we can write as Kc is equal to concentration of C, that is 0.35 square, divided by concentration of A is 0.325 into the concentration of B square, that is 0.4 square. If you simplify this, you will get the answer as 2.36 mole per liter. Okay.